We've had a lot of questions, a lot of interest over hydrogen embrittlement over the last 6 months in particular. So the first question I have is how do rapid screws perform in terms of hydrogen embrittlement risk?
Okay, this is a quite interesting question. And as far as I know, the company Schmid Schrauben sells their fully threaded, high efficient rapid screws for about 20 years now. And in this time span in Europe, I mean, and in this time span, I've never heard of any of the screws failing by hydrogen embrittlement, even though these rapid screws have a rather high steel hardness. We come, I think, in the frame of the interview later to this point back again, and our strength. So from an empirical point of view, one can conclude that these rapid screws have a rather low risk in terms of hydrogen embrittlement. From a more scientific point of view, from a more quantitative point of view, I can tell you that we in Graz have carried out 2 research projects about hydrogen embrittlement of self-tapping screws in the past, both together with Schmid Schrauben. Thereby I can summarize that this low risk of hydrogen embrittlement, which can be observed over the last 2 decades of screw application, could be confirmed also on this scientific level. So far, the boundary conditions regarding a secure screw application are kept. What does that mean? Amongst other things, this means that the screws should be inserted with torque control devices when creating steel to timber connections, for example, or metal to timber connections in general, or that the timber members should not get too bad in the time frame between the off-site screw installation, I mean the screw installation at the manufacturing plant, and the on-site erection of the timber construction. So wetness in this situation or in this phase of the construction should be avoided as good as possible.
Right, and then I guess just one small clarification. You said that the rapid screws have been manufactured for 20 years, and that's just the Rapid brand. I know that Schmid has been manufacturing for much longer.
Exactly, yes.
Okay.
So I just wanted to focus on the rapid fully threaded screws.
So the next question I have for you, there is a CSA standard that has been published recently in Canada, CSA standard 086 2417.6.4, which talks about the allowance of, I guess, hardening standards in the Canadian code. Can you give us some context on the origins of the standard, what the standard was based on?
Well, I'm not an expert in Canadian standardization, of course, because my focus lies on the European research, but I can assume that these limitations were introduced to prevent the hydrogen embrittlement of self-tapping screws. As far as I know, the Canadian colleagues had to observe some sudden and brittle damages of screwed connections in the past, and that hydrogen embrittlement could be detected as a failure reason of these damages. And we know that the risk of hydrogen embrittlement generally increases with an increasing hardness and/or steel strength. So the limitation of a core hardness value of such screws, of case hardened screws, as it is given in this section, is then an obvious logical reaction to face this problem.
You know, when we read that CSA 086 standard, read that it exclusively considers case hardened screws. Are there any other heat treatment measures which can lead to hardness distribution?
Yes, this is a very important point regarding that standard. So obviously, the new and currently valued of this CSA standard only considers case hardened screws in terms of hardness limitations. This is very important for us. However, there are other ways to produce and harden carbon steel self-tapping timber screws. One heat treatment measure which is applied by European manufacturers, such as Schmid Schrauben, for example, is austenitization and quenching. So the A and Q. And A and Q leads to a rather constant or uniform hardness distribution over the screw's cross-section and consequently to different mechanical performance than case hardening.
So what specific benefits does uniform hardening offer over case hardening in timber screw applications?
So typical uniform hardness distributions can be characterized by somewhat higher core hardness, yes, and a significantly smaller surface hardness than the distributions which are the results of case hardening. For mechanical properties which benefit from high steel strength at the outer zones of the cross-section, such as the torque or the yield moment of the screw, the uniform hardness distribution has at the first glance, let's say, a disadvantage if compared to the non-uniform one. So, but why are we applying this uniform hardness distribution? Because in practice, the difference of the torque, for example, is not that big and less relevant than the big advantage of a lower surface hardness, which is the higher ductility. So the higher ductility is the consequence of this uniform hardness distribution. And the higher ductility is beneficial to generally prevent sudden and brittle screw failure in general. This must not have to do with hydrogen embrittlement, so it's a more general thing, and especially in terms of cyclic loading, which means seismic or fatigue design. Yes, and so far we found out, in addition, a lower surface hardness, so back to the topic hydrogen embrittlement, is also very advantageous in terms of hydrogen embrittlement. The latest tests, for example, we carried out with our electrochemical charging cell at Graz University of Technology. This charging cell allows us to quantitatively load the screw with hydrogen for the first time, I would say, led to the interesting result that a screw with a uniform hardness distribution in the core hardness above 390, according to Vickers, has an about 35% higher tensile resistance than one with a core hardness distribution, with a core hardness value smaller than 360, according to Vickers, but significantly higher surface hardness. This first finding shall point out the importance of a low surface hardness or the advantage of a uniform hardness distributions in terms of hydrogen embrittlement. And this low surface hardness is, from my point of view, more important than a core hardness limitation.
Which production steps does Schmid take that could cause a hydrogen diffusion?
Okay, so you mean, I think you are pointing out the internal hydrogen embrittlement, yes?
Yes, that's
this
right.
Was one of the main research objects we focused on in our last research projects regarding hydrogen embrittlement. This is called SCREW, HISCC, hydrogen-induced stress corrosion cracking. And thereby we focused a lot on the hydrogen absorption during the screw production. This was made, I want to point that out, in the frame of a master thesis by our student Alexander Vujic. Thereby he had two main findings. First, the maximum hydrogen uptake took place after having finished the hardening process. This is quite interesting. While in the frame of galvanization, no real increase of the hydrogen content could be observed. This is interesting because in many studies, the galvanization process is the vulnerable step in the production. And second, he could observe a quite fast desorption, so the loss of hydrogen, the very advantageous loss of hydrogen, when the screws are stored in normal atmosphere after galvanization. So if you just store the screws after galvanization and wait for some time until we use them in the construction, we lose this disadvantaged hydrogen already. So after approximately 1 week, the hydrogen content decreased to 1/3. And after about 2 months, there was no relevant hydrogen content left in the sample. Internal hydrogen embrittlement is a matter of time, of storage time, let's say. This is one of our conclusions. And
Right.
it is worth pointing out that the results are currently only valid for the production process of one manufacturer, because we just examined the manufacturing process of Schmid Schrauben. For a more general conclusion regarding that, further production processes should be examined that way.
So one thing you said earlier in terms of the hardening process was the observation of hydrogen content. So obviously hydrogen is too small to observe, with our eyes. What scientific methods are you using to determine the screw's hydrogen uptake as an indicator for internal hydrogen embrittlement, and how reliable are these methods?
That's a good point. And in the frame of these research projects, not only of the SCREW HISCC, but also some other ones, we are collaborating with colleagues from the Institute of Material Science, Joining and Forming of Graz University of Technology, because they are the experts in this field of timber screw application. And they measured for us the hydrogen uptake by a so-called thermal desorption analysis, TDA in short, using a thermal conductivity detection. You can imagine I'm a structural engineer and I'm not that deep into this topic, and I explain it to myself by a heating process, which releases the absorbed hydrogen if we heat the sample, yeah, and which can then be measured by a certain device, which measures the content of the heated air, for example, yes. And in general, this method is well approved in machine engineering, for steel engineering or machine engineering with steel products in general, but it took us a really long time span to apply it for self-tapping screws in a reliable way, because you mentioned it already. It should be, of course, reliable, and it should be repeatable. Not only at Graz University of Technology, should be repeatable all over the world. And so I think, but in the meantime, I think we have established it, and we can use it also to determine the hydrogen content of a sample after this electrochemical charging. So it's currently part of our methodology regarding the research of hydrogen embrittlement.
What in real world environments, can you explain how significant the threat both of these hydrogen embrittlement is?
Yeah, that's a very important point, because this is also the task of our future focus on research activities. And I can tell you, to conclude from the research activities done in the past, that so far the applied production process is quite comparable to the one we examined for Schmid Schrauben. That means that the galvanization won't lead to an increase of hydrogen content, and that the hydrogen desorption, the advantageous loss of hydrogen afterwards, takes place as observed. I would say that the external hydrogen embrittlement is far more vulnerable than the internal one. Yes. The main reason is that we know already a lot about the risks of the production process, and I would say we are able to control it, e.g., for example, by this thermal desorption analysis. While the on-site application of self-tapping screws contains some open questions, yes, which have not been answered so far, at least for me. What can these questions be? This is the impact of the ocean freight, for example, the atmosphere during the transport over the ocean, the storage at the building site, the rainfall during construction, and so on. And this has to be clearly pointed out. If the right production process is given and the boundary conditions for a secure screw application are kept, the risk of hydrogen embrittlement is in fact rather low at all. So it's not an everyday problem, hopefully, of course not. It is not without a reason that this connection technology has been applied in Europe very successfully over the last 20 years. So if we would have observed hydrogen embrittlement in many more cases, we would have changed this connection technology. From my point of view, this connection system with self-tapping screws works quite well, but such special topics such as this hydrogen embrittlement have been kept in our mind, and we have to do more detailed research about it.
Right, and I do recall you mentioning that in the past, Schmid Schrauben had used a case hardening process, but moved specifically to the quenching process. One of the main reasons was a better hydrogen embrittlement management.
I've heard something like that. So I think back to the 80s and 90s, this case hardening was also applied in Europe as well. Also, I think if I'm right, it's Schmid Schrauben, but they changed this hardening or heat treatment process just a long time ago, and one of the reasons was this embrittlement of the steel product in general. So as I mentioned before, you lose a lot of ductility of the steel if you do this case hardening, if compared to austenitizing and quenching. And these are results why they changed this production method, and they have now, let's say, a more reliable and more secure screw.
Anything important to add that we haven't yet discussed?
Yes, as we are still working on the topic of hydrogen embrittlement, and so hydrogen embrittlement of steel products in general is a very complex research field, and many dissertations are currently ongoing, even in Styria, one of the countries of Austria. So you can imagine that we have not finished our research activities on hydrogen embrittlement of self-tapping timber screws so far. So at the moment, we are, for example, preparing a new research project which deals with a broad application of this electrochemical charging method. Okay. Amongst others, because at the point we are now, we just examined screws without coatings, for example. We want to now check the impact of the coating type more in detail. So this will be a project where we link the two very main important topics, which is the corrosion process itself combined with hydrogen embrittlement. And to work on this project, I'm really looking forward to.